Okay, this is a probability video for my pre-algebra students. So on our first page, we are asked to look at probability on numbers. And the first question says this. So a number is chosen at random from 1 to 50. And we need to find the probability of selecting an even number. Well, half of these numbers is even. Half of these numbers are even. So 25 out of 50 numbers is even. That's our chance. That's our probability of getting an even number. We can reduce that to 1.5. So we could say we have a 1 in 2 chance, a 50% chance. Here on this page, we're looking for a fraction for an answer. So a 1 in 2 chance, probability of 1 in 2 for getting an even number. Let's look at another one. So number 2 on our first page is asking us to find. Says that there's a number chosen at random from 1 to 25. We're going to find the probability of selecting a number less than 4. Okay, so it's less than 4. What numbers? How many numbers are less than 4 out of 25? Well, there are 3. 3 numbers that are less than 4. That doesn't include 4. And what are the total possibilities? There are 25 numbers. So that's it. 3 in 25 probability or chance that we can select a number less than 4. Okay, let's try one more on this page and then move on. A little further down on the page, we are given a number is chosen at random from 1 to 50. Find the probability of selecting numbers with the last digit of 7. Okay, well, we know we have 50 numbers altogether, right? So we can write that as the denominator. And we need to think how many numbers have a last digit of 7. Well, from 1 to 50, we have, just list them over here, we have 7, 18, 27, 37, 47, right? So, and I really think that they also meant to include 7. And the way that this is worded, sometimes it's a little ambiguous. But if we look at it this way, we have 5. So 5 out of 50, we can reduce to 1 over 10, right? And so this is the probability of finding or selecting a number with the last digit 7. All right, so let's move on to probability with a single die. So we have one single die here that I actually don't know the known order, so I'm just going to do random dots. Okay, single die. And we're asked this. We are asked to find the probability of rolling a 2 or smaller. Well, we know that in any given roll, there are 6 possibilities. So we can go ahead and put 6 down as our denominator there in the ratio. So, well, how many numbers are there that are 2 or smaller? We have 1 and 2. So now we can reduce this ratio. We have a 1 in 3 probability of rolling a 2 or smaller. Let's try another one. And number 4 on this page with the single die, we are asked to find the probability of rolling a divisor of 6. So let's think, what are the divisors of 6? Well, 2. Perhaps we could include 1. 3. And 6 itself. So we have 4 possibilities that are divisors out of the 6 that we could roll. This reduces to a 2/3. So we have a 2 and 3 probability of rolling a divisor of 6. Let's move on to the next section, probability with a pair of dice. Now we're asked to find the probability of rolling factors of 5 on both dice. Now, we'll try not to overthink this. First, what are the factors of 5? Factors of 5. Well, 1 and 5. What are all the possible outcomes? When we roll the dice, there are 36 possible outcomes altogether, right? I don't want to write them all down here, but 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. And it just goes on and on and on. 2 and 2, 3 and 3. And we could just make a continuous list. And you can chart that, you can graph that if you want. So 36 is our grand possibility. Like how many different altogether rolls that you could have. And they're asking you to find probability of rolling factors of 5 on both dice. So a 5 and a 5. They want to know what's the probability? What are the chances of you rolling a 5 and a 5? Well, I have to think that a 5 and a 5, or a 1 and a 1, or a 5 and a 1, a 1 and a 5. Those are all the factors of 5 on both dice, all the possibilities, right? How many of them are there? There are 4 of those possibilities. Now this is something that I can reduce. 1 in 9. And this is the probability of rolling factors of 5 on both dice. Let's look at another one. Number 3 on this page asks us to find the probability of rolling a prime number on both dice. So, the first thing that we need to think about is that, again, it's 2 dice. So 2 dice, we have, still we're writing it out of 36, okay? And we can also, let's decide what numbers are prime from 1 to 6, right? Those are the numbers we're looking at, from 1 to 6. We're not going to include 1. This was a mistake that I had made for a while, and I stared at it and went, what? Okay, but do not use 1. So, that in mind, 2, 3, 4, I'm sorry, not 4, definitely not 4, because that has factors. So remember that a prime number is a number whose only factors are 1 in itself, okay? All other numbers are composite, like 36 is composite, 4 is composite, 6 on the die is composite. Okay, so we have 3 numbers that we could possibly roll that are prime. And we have two we have two ways to do this, actually. So you can think of it this way. We have 3 prime numbers out of 6 total sides, right? We can reduce that to 1/2. Now we can, because we have two dice, we want to multiply 1 dice by 1 dice. And that gives you 1/4 and you're done. So the other way you can think about this is you have 36 total possible combinations, right? And so this 3 here represents a possible roll for 1 die. For 2, it's 3 times 3 is 9, right? So then I would take this, represents my probability, but if I reduce it, 9 goes into 9 once, 9 goes into 36 4 times. And you can see that I have come up with the same probability, the same ratio there. So I have a 1 in 4 chance of rolling a prime number on both dice. Let's look at another one. Here's the next problem. Find the probability of rolling factors of 2 on both dice. So 2. What are the factors of 2? Well, the factors of 2 are, 1, 2, and 4. Now, if we're not going to include 1 as a factor, and this is a matter of semantics, that changes. So this is kind of vague. So I would assume that perhaps they are not looking for us to omit 1, but if we are looking at the factors strictly not including 1, it would be the 2 and the 4. So let's solve this both ways and see what happens. So if we look at factors being 3 factors out of every 6, right? Reduce that to 1/2. And we have 2 die. We get a 1 in 4 chance or probability. If we look at factors, the probability of rolling factors of 2 on both dice as just being 2 and 4, we have 2 possibilities. Out of the 6, that reduces to a 1/3, and we have 2 dice, so that gives us a 1 in 9. My students, I want you to think about 1 being a factor. Technically, 1 and the number are factors. So let's focus on this being the right answer. Okay, let's move on. Let's move on to the next concept. Okay, so fixed. Okay, find the probability of drawing a 10 of diamonds on the first draw, replacing it and drawing a spade card on the second draw. So this page of probability problems deals with using a deck of cards, and the questions are all based on a 52 card deck without jokers. Okay, so let's keep that in mind. 52 cards and no jokers. We are playing with a full deck. That's why there are no jokers. I'm just kidding. Okay, so let's break this down. In a deck of cards, we have diamonds, we have hearts, we have clubs. And then we have spades. Of course, each of these suits has an ace, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have a jack, queen, and king, right? They don't repeat. So there is only 1 10 of diamonds in this deck. So what are we trying to find? Well, the probability of drawing out a 10 of diamonds, the first draw is a 1 in 52 chance, because there's only one of those in the entire deck. And they're asking, find the probability of drawing a 10 of diamonds on the first draw, replacing it and drawing a spade card the second draw. Okay, so we replaced it, right? So we still have 52 cards. If we didn't replace it, this would be a different math equation. But we did replace it, and so we still have 52 cards. After replacing that 10 of diamonds, we have 52 cards. And there are 13 spades. Okay, 13 of those spades. And there's no specific spade that it's asking us to find, just drawing a spade. So what are the chances? We are going to draw a 10 of diamonds and then draw any spade on the second draw. So because there are 13, that is a 13 in 52 chance. Now that, believe it or not, actually reduces to 1/4. Now we have to combine these two probabilities, right? The draws were independent, right? Remember that independent means that the first outcome does not impact the second outcome or the third, and so forth and so forth. So we can simply multiply 1/52 times 1/4. And I'm going to get my calculator here. A 52 times a 4 gives us a 208, and the 1 stays a 1. So we have a 1 in 208 chance of first drawing a 10 of diamonds and then replacing that card and drawing a 10 of spades the second time. Not great odds. Better odds than winning the lottery, but still not awesome. Let's try another problem on this page with a deck of cards. So now we're asked to find the probability of drawing a face card. We still have the 52 cards, right? So let's discuss, what is a face card? Is it a happy face card? So in a standard 52 deck card, without any jokers, the face cards are the jacks, queens, and kings of each suit. So because there are 4 suits, hearts, diamonds, clubs, and spades, each suit has 3 face cards. So 4 suits times 3 face cards gives us 12 face cards altogether. So remember, we put the number of favorable outcomes over the total number of possible outcomes. Well, favorable outcomes, 12 over the 52. And that will reduce So this can be reduced. 4 goes into 12 3 times. 4 goes into 52 13 times. So the probability of drawing a face card is 3 in 13. You have a 3 out of 13 chance of drawing a face card out of a 52 card deck. Let's try one more of these. Number 7 asks us to find the probability of drawing a 9 of clubs on the first draw, replacing it, and drawing a black card on the second draw. So, a 9 of clubs, so we have 2 different draws here. So how many black cards are there? Maybe let's talk about that first. So half the deck is black. 26 cards are black. So we'll just write that out first. That's the easiest part. 26 out of the 52 cards are black cards. All right. So drawing a 9 of clubs on the first draw. Let's talk about that one. So that's a unique card. That's 1 out of the 52. And these are 2 events that are independent, right? Because it does say replacing it and drawing a black card on the second draw. Since these events are independent, the probability of both events happening in this sequence is the product of individual probability, and we can go ahead and multiply these 2 probabilities together. Oh, let's reduce the 2650. That's 1/2. So before why multiply such large numbers? That's just 1/2. Okay, so what does this make? 52 times 2 is 104. So we have a 1 in 104 chance. This is the probability of drawing a 9 of clubs on the first draw, replacing it, and then drawing any black card. All right. So let's move on to spinner probability. Okay. Yes, this is a spinner. It's a bit odd looking, but let's pretend it's beautiful. And when we spin it around, we have the possibility of landing on an A, a B, a C. Oh, there are no D's, but we have E's. Okay. So what is the probability of the spinner landing on A or B? So the first thing that we need to do is figure out how many of each of these letters there are. For some reason, and this is from the worksheet, probability using a spinner, number 1, and they do not have any D's on there. Okay. So, how many A's do we have? Let's see, 1, 2, 3. How many B's do we have? There's 1, 2. Just the 2 B's. And how many C's? Well, I only see 2 C's. And for the E's, I see 3. So checking that again. I see 3 A's, 2 B's, 2 C's, 3 E's. Okay, so that's important to start with. And how many altogether possibilities do we have? Looks like there's 10, right? 1, 2, 3, 4, 5 on each side. So out of 10 possible. So for this one, we want to think that we're looking at an OR here. So we kind of want to sum them together. So the A, we have 3 A's, and the B's, we have 2. So that's 5, right? And so number of favorable outcomes over the total number of outcomes. That would leave us with 5 over 10. And the probability would reduce to 1 in 2 chance. Right? A 5 and 10, a 1 in 2 chance there. Okay, let's look at another possible spinner question here. Kind of want to leave that spinner there so I don't have to redraw it. Let's look at number 7. What is the probability of the spinner not landing on C? So this is C. We have 2 out of the 10, but not landing on it represents everything else. So it represents the 8 out of all the 10 possibilities. And then we reduce that to a 4 and a 5 chance, or 4 to 5 chance, the probability of the spinner not landing on C. That's everything but that C. Okay, piece of cake. So you've got this. The last section on our homework deals with operations with scientific notation. And we have been covering fractions, rational expressions that have exponents on various values, including all of your variables, where we are multiplying and dividing those exponents. So we want to kind of do a little bit of that here. Okay, so you have scientific notation, which is representative of either a really small number or a really big number, right? And we use scientific notation to help us not carry on decimal points or zeros across a page. It's a way to make everything a little more succinct and manageable when it comes to numbers. We use this in science, thus scientific notation, quite often, whether it's chemistry or astronomy. Anything very large, anything very small. Okay, but our rules of exponents apply here. If you do not remember how to think about scientific notation, I suggest that you review what it represents. So, with this, simply the best solution, the best way to approach this is to take the number, these numbers, and here you are not multiplying, you're dividing, right? So this is number 1 on the page, by the way. So we have our 1.16 and our 3.1. Now you're going to have to think about your rules here. Hopefully you learned a long time ago. You're going to move that decimal over. When we divide, we deal with those decimals, moving them right away. Okay, it looks like it's probably going to still be a very small number. So 11.6 divided by 31. 31 will go into 106 about 3 times to start with. 3 times 1 is 3, and then we have a 9 here. We do our subtraction. 6 minus 3 is 3. 11 minus 9 is 2. And now we drop our 0. 31 won't go in 10 times, and it'll probably go in about 7. So 31 will go into 231. Let's see, 7 times 1 is 7. 7 times 3 is 21. And we borrow, of course, 10, showing every step here. And we have 13. Well, how far do we go? As far as we need to right now. I want to go a few more place values, and here's why. When we convert it back to proper scientific notation form, we're going to need a little accuracy. I would say thousandths place is good. Okay, so you can stop at the thousandths place. You can round. So let's make a little note of that. Round to the thousandths place. Okay, this is for this entire page, so my students know. All right, again, another 0, drop it. And so it's about half as many times it looks like it'll go into, maybe 4. 4 times 1 is 4. 4 times 3 is 12. Pretty close, pretty close. And we have 6 left over. Now, if I move that decimal place over 1 for my scientific notation, I still need another place value. So what am I going to do? Another 0. Okay. Oh, it'll go in almost 2 times, but we have to settle for a 1. Bummer. I'm going to do one more. And, oh, that's almost, 29 is almost 31, so I'm going to try 9. 9 times 1 is 9. 9 times 3 is 27. That looks pretty close there. And of course we borrow, knock on that door, and we have 11. Okay, I'm going to stop there. So that should give me a decent thousandths place value. Let's see. So we did the division of this, and we have the 3, 7. Oops, I said 3, and I didn't write it. What a funny thing to do. All right. Now, this part needs to be treated with our exponent rules, right? So what are our exponent rules? Well, this is essentially 10 third power minus 5, 3 minus 5. So it's a negative 2. However, we're not done, because if you remember, scientific notation needs to be, absolutely needs to be in this first part, needs to be between 0, so in other words, it needs to be greater than 0, okay? But it also needs to be less than 10. So let me just say, I'm going to say it this way because I think that might be confusing. Let me try that again. A 1 equal to or greater than a 1. That'll do it. And then, of course, it definitely needs to be less than 10. So what does that mean? That means that we have to take this decimal place and move it over 1. So we have a 3.7419. And when we move a decimal place to the right, we need to adjust this. So this goes, be careful how I say this, it goes down 1, which makes the digit itself go up. So it is to the negative third power now. That is our answer. And I said to the thousandths, right? Tens, hundreds, tenths, hundreds, thousands. So let me readjust this. 4, and then that would round up to 2. There's the answer that we're looking for. All right. this one. All right, it's rounded. So it was good that I went this many places, right? I know it looks tedious, but this is what you need to do. All right, there are only 12 problems on that page. This was a division one. Let's practice one of the multiplication ones, and then we'll be done. So let's look at number 8, which is multiplying these two numbers in scientific notation. Notice that they're both negative. Okay, so first, what are we doing? Let's look at this. Well, 8.6 times 6. 6 times 6 is 36. 6 times 8 is 48, plus the 3 is the 51. We'll move over our decimal place, and we have a 51.6. Now we can concentrate on this, right? When we multiply exponents, what are we doing? We're adding them, right? So basically, -4 plus a -6. Now we're adding negatives, so we're becoming more negative. This number doesn't magically become positive. This exponent does not magically become positive. So this is 10, and that is a -10. However, here we are looking at this. The number is 51, and this is not in scientific notation because it is not greater than or equal to 1 and less than 10. So what do we need to do? We need to move this decimal one place to the left, giving us 5.16. What does that do to our exponent here? Okay, so we'll move to the left. When we moved to the right earlier, we took up, because it's negative, we took this -2 and it became a -3, right? We took one away and we moved to the right. So here, moving to the left, we're going to add 1, but don't let the negative confuse you, because if we add 1 to that -10, it's now a -9. Sometimes a little tricky to explain and to work these through and wind up with the correct negative exponent. Now this is a really, really small number, right? To the 9th power. Lots of zeros. This would be a decimal point and then 0. So just for kicks for this one, let's make this into standard form so that you can see what this looks like. So if you write this out, the way to do it is to count now 9 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and that's where your decimal goes. And I'm not able to draw that so easily because I have sidebars in my way. Okay, so there's the decimal. 2, 3, 4, 5, 6, 7, 8, and then the 5. Yep, that's the number. Isn't it so much better to write it this way? Of course it is. All right, so good luck on your homework pages and have an incredible week. Miss April will see you soon.